Hi, how's everyone doing today? Doing pretty good. Doing pretty good. Happy it's Friday once again, even though it feels like snuck in a couple extra days this week, just like last week. Um, okay, so first order of business. So as you should be aware, next Tuesday is the next exam. So this is the last material we're going to be covering for the exam. Y'all know the drill by now. It's going to work exactly like it has previously. I'll do the review session on Monday during class and through, for another hour or so afterwards. So the exam review questions I just posted under files in the usual spot. So under exam review questions. Same deal as last time. I will write up those solutions this time. I will make sure I do it with a clear head. So I won't be doing this with half a bottle of wine in me this time, because that was a fiasco last time. My bad. Also, there's some really useful things I want to cover to help simplify integrals using symmetry. But I'm not going to have time today. So I am going to make another lecture, and I will post it to the YouTube. I'm going to say that should be up by tomorrow afternoon. It's very useful, and it'll save you a lot of time if you get good at doing this. But I don't have time today to go through it. But it's a very useful thing, and definitely suggest watching that and getting in the habit of using the symmetry to simplify integrals. Yeah. I'll let you know when it's up. I'll send out the usual emails. I'll mention the review session, but yeah, I'll do that. I'll do that. But yeah, so exam review questions are currently up in Canvas under files and subfolder exam review questions. But yeah, any questions? Okay, so let's get rolling. Okay. So we're going to look at applications, multiple integrals. Really, it's just going to be finding mass, center of mass, and average value of the function over a region. Okay. So normally, I would sort of go through where these equations come from, these integral expressions, but definitely don't have time this semester, and honestly, I probably don't need to spend as much time as I usually do deriving this stuff. So let's just jump right into it. So suppose Um, we have a density function delta. So, whoops, delta is a function giving the density of so it could be the density of several things. It could be the mass density. Don't need to put that in parentheses. So the mass density, population density, so like the charge density, etc. Any kind of density. In some region. So either in some region D and R2, we like to call regions in R2D for some reason, or W and R3. So delta can be a function of 2 variables or a function of 3 variables. Right. So if it's density on some region D, so we usually think of it like if it's like mass density, we think of D being like a plate, a thin flat plate in R2, we call it a lamina. And it gives the density at each point, right? Delta of XY. Oops. So the total amount of stuff, so we have the density of whatever we're talking about. So the mass density, the population density, the charge density. So if we're given a density function, right? So think population density, right? So if you have some area in R2, and we have a population density, if we want to find the total amount of whatever we're talking about, in this case, population, the total amount is just the integral of the density function over the region. So the total amount of mass, population, charge, whatever we're talking about, is the integral of the density function. So if we're in R2, it's the integral, the double integral over the region in R2 with respect to area. If we're in R3, it's the integral of the density function over the region in R3. So total amount is integral of the density. And it's a double integral if it's an R2, triple integral if it's an R3. Okay. So let's look at an example. So let's find the mass of the solid bounded by the paraboloid, so the elliptic paraboloid, z equals some constant a times x squared plus y squared and the plane z equals capital H, where here a and h are just going to be positive constants. And the density, so the mass density here, because we're talking about mass, is just going to be z. So we want to find the mass of this solid region, the total mass, and we're given the mass density. Okay, so lots of things we got to do here. So let's sketch the region and figure out what we're integrating and then what coordinate system we want to use, et cetera, and then find the bounds. Okay, so we have a paraboloid, z equals some positive constant a times x squared plus y squared. So that's going to be a paraboloid opening upwards with z-intercept the origin. And it's also bounded by the plane z equals h. So that's going to go until it hits the plane z equals h, which is just parallel to z equals 0, which is the xy plane. So this is our region W. It's the solid region inside there. So this is z equals h. This is z equals a x squared plus y squared. Okay, so oops. How do we want to proceed here? So we're doing triple integrals, so we can either use rectangular coordinates and say there's a top and bottom, left, right, or front and back surface, or we could use cylindrical coordinates. Remember, we like to use cylindrical coordinates if there is symmetry about an axis, or or we could use spherical coordinates if it's bounded by spheres or cones or spheres and something else usually. So how do we want to proceed? What coordinate system would we like to use here? Rectangular, cylindrical, spherical. What do you think would be easiest? Cylindrical is good. We don't want to use spherical because there are no spheres here. This guy down here, it's a bad drawing, to be fair, but that's a paraboloid and not a sphere. So if you don't see a sphere anywhere, I wouldn't mess around with spherical unless the question explicitly says use spherical. So let's say cylindrical makes sense because this guy is symmetrical about the z-axis, right? Just rotate this guy around the z-axis. Okay. So we're using cylindrical. So we need bounds for z, r, and theta. Okay, so remember, so for z, z is easy, usually. So z is just the normal z. So we have a top surface and a bottom surface. We need to write those as z equals something, but we need to convert x and y into cylindrical. So there should be no x and y. It should just be an r and theta. So z is bounded above by z equals h. So that's easy enough. So that's the top surface. How do I write the bottom surface in cylindrical? So we have z equals a times x squared plus y squared. What does that become in cylindrical? Right. Well, a times r squared, right? X squared plus y squared is r squared, and we have a times r squared. Okay. So we have our bounds for z. So when we're finding the bounds for r and theta, oops, just remember r and theta are the same as in polar. So what we're going to do is we're going to project down to the xy plane. So the way we're going to do that is let me actually give myself more room here. Okay, so we want to find the shadow of this guy in the xy plane. So the thing we want to see is the outer boundary. The outer boundary is going to be like the widest part. So what is the widest part of the shadow going to come from? So where in the figure is the widest part? Where in W? Right, so it's going to be at the top. And so the outer curve is going to come from the intersection of the two surfaces, right? The intersection of the plane z equals h and the paraboloid. So we need to figure out what the projection of this guy to the xy plane is. So we want to find the intersection of z equals h and z equals a x squared plus y squared. Or actually, we changed it to cylindrical, so let's keep it like that. Z equals a times r squared. Okay, so the intersection of z equals h and z equals a times r squared, well, set the right-hand sides equal to each other. H equals a times r squared, and we want to get bounds for r here. So r is equal to h over a. Hang on. So r squared is h over a. And so take the square root. R is the square root of h over a, plus or minus, but we're taking r to be positive. So when we project this down, we see we get a circle, right? The radius of that circle, it turns out, is going to be square root h over a. So from the picture, we see r goes from 0 out to r equals square root h plus a, which is that circle there. And how about theta? Theta goes from what to what? Zero to 2 pi, because we get the entire circle. We go all the way around. All right. So any questions about how I got the bounds for, say, r here? We projected down. It turns out we didn't really need to. Actually, it's still good to draw a picture. Still good to draw a picture. But we figured out exactly what that circle was, the outer boundary circle. It's the intersection of the two surfaces, and we see it has radius square root h over a. By finding the intersection, solving for r. Okay, so let's set up the integral, and then I'll just tell you what the solution is when we evaluate it, because that's the important part, is setting it up. So the mass, we said, is the integral over the region W of the density so we said the density was Z. Yes. So we integrate the density over the region W. So we found the bounds for W. We're going to convert this to cylindrical. So we said theta goes from 0 to 2 pi. R goes from 0 to square root h over a. And Z goes from AR squared up to h. Okay, so Z, the function Z, we need to convert to cylindrical. Z becomes Z, X becomes R cos theta, Y becomes R sine theta. Well, clearly this is still Z. And what is dV and cylindrical? If you don't have the values for A and H, well, A and H are, they stay A and H. So the solution is going to involve A and H, but it just means you can plug in whatever value you want for A and H. Yeah, they're constants, but they're not defined explicitly. Yeah. So what is dV? Well, careful, we're not integrating. Just what is dV in cylindrical before we integrate? R dz dr d theta, right? Can't forget the R. Okay, so this is not a difficult integral. The important part is setting it up. So what we get is the mass is, so pi h cubed over 3a. the important bit was setting it up, seeing it had symmetry about an axis, so cylindrical is a natural choice, and no spheres involved. So spherical doesn't make sense. And then knowing how to find the bounds for z, r, and theta. Okay, any questions about this? Just remember, mass, total amount, right? If you have a density, you want to find the total amount, the mass, population, charge, etc. You just integrate the density over the region. Okay, so let's look at center of mass. Oops. Got more room now. Okay, so suppose the same thing. Suppose we'll do the example in R2. So suppose we have a lamina, just so you know what that means. So think of it as a thin, flat plate. So some lamina D and R2 in the plane. And we're given a mass density function. So, sorry, has density. So we have some plate in R2. We have a density. We want to find the center of mass. So I'm not gonna explain exactly what a center of mass is. You can look that up if you like. But the center of mass is some point on here. X bar, Y bar. And we're going to find each coordinate separately by doing integrals for each. So it's going to have coordinates. The x coordinate of the center of mass is going to be, you integrate, instead of the density now, you integrate x times the density. And then this is important, then you divide by the mass of D. And we saw how we find the mass of D. You just integrate the density. Over D. So to find the center of mass, you actually need to do 3 integrals. You need to find the mass first, and then you do an integral for the x coordinate and an integral for the y coordinate. And then the y coordinate's the same thing. It's 1 over the mass times the integral of now y times the density. So for center of mass problems, you need to find the mass of the region, And then for each coordinate, you do the integral of whatever the coordinate is times the density over the region D, and then you divide by the mass. Right, so 1 over the mass, integral of whatever the coordinate variable is times the density. And the same works for R3, right? So I'll just write this really quickly. So some region W in R3, whoops. With density delta x, y, z. Has center of mass x bar, y bar, z bar. Same thing. X bar is 1 over the mass times the integral over W of x times the density. Y bar is same thing, y times the density, 1 over mass. And then z bar is, of course, 1 over the mass, integral over W of z times the density. Where m, of course, is the mass of W. Okay, so exact same thing. Just integrate, divide by mass, and integrate the variable for the center of mass times the density over the region. Okay, so let's do an example. Sure. Alrighty. So let's find the center of mass of the lamina, the thin flat plate D, which is bounded by y equals 1 minus x squared, and the x-axis and it's going to have density y. Okay, let's, as always, sketch our region, figure out how we want to proceed. Okay, so it's bounded by the parabola y equals 1 minus x squared and the x-axis, right, y equals 0. So y equals 1 minus x squared, the parabola pointing downwards, or opening downwards rather, with y-intercept 1. And it's gonna hit the x-axis at -1 and 1. So it's bounded below by the x-axis. So pretend this is symmetrical here. So that's our parabola, y equals 1 minus x squared. And this is the x-axis, which we'll label in a second. Okay, so we're in R2. We're in the plane. Well, let's figure out what we're integrating first. First, we need to find the mass. So the mass is just the integral over d of the density. Let me just do this. Which we said is y. So we integrate the density over d to find the mass. Okay. So we're integrating over d. All right, so we're in R2. So we have two options. We could do rectangular, I guess sort of three options, right? Rectangular, and if we're doing rectangular, we find a top curve and a bottom curve. So it's vertically simple, or a left curve and a right curve, horizontally simple. So either rectangular, or we do polar if it's bounded by circles and stuff, which makes sense. Rectangular, and if it's rectangular, do we want to have a top curve and a bottom curve, or left curve and right curve, or do we do polar for this one? Right, so we want to do rectangular, and there's a top curve and a bottom curve, right? It passes the vertical line test. It doesn't make sense to do polar in this case because there's no circles anywhere, and generally that's the only time we're going to be doing polar. Right, so rectangular with the top and bottom curve. So the vertical variable y is going to be bounded by functions. So we're bounded above, we see by the y equals 1 minus. Why do rectangular if we're looking at a plate? I'm not sure I understand. So plate is a plate can be any shape. A plate is not like a dinner plate, like circular or anything like that. I don't know if you're getting hung up on the term plate. It just means some thin flat region. Yeah. Maybe that's maybe a slight misnomer. Not misnomer, but I could see the confusion there. But yeah, we're just talking about some region in R2. Yeah. So we're bounded above by y equals 1 minus x squared. So that's the upper bound. And what is the lower bound? Y equals what? What's the lower curve? 0, right. So those are the bounds for y. Y is bounded by functions. X is going to be bounded by numbers. So x goes from what to what?
-1 to 1.
From -1 to 1. Okay, so we have our bounds. So x goes from -1 to 1. So y is bounded by functions, so we integrate with respect to that first. It goes from 0 to 1 minus x squared. And we're integrating y. And so dA becomes dy dx. So dA is dy dx or dx dy in rectangular. The order depends on whether you have top and bottom or left and right. And so that's a straightforward integral. That is just going to be 8 over 15. 8 over 15 is our mass. Okay, so it's not asking for the mass, but you need to find the mass in order to get the center of mass, because you have to divide by the mass after you do the integral. Okay, so we found the mass. Let's find the coordinates of the center of mass now. Let me do x on here. So it's 1 over the mass times the integral over d of x times the density okay, so 1 over the mass, well, we said the mass is 8 over 15, so 1 over the mass is 15 over 8. And then we've already found the bounds for our region of integration, so we just use those over again, thankfully. That's a nice thing, is once you've done that, found the mass, you've done the hard part. You found the bounds and everything. And you can use those same bounds because you're still integrating over the same region. So x goes from -1 to 1, y goes from 0 to 1 minus x squared. So then it's x times the density. The density's y in this case. dy dx. Okay, so here I'm going to wave my hands a bit. I'm not going to explain it here. I'll explain this on the next video I upload sometime tomorrow. But we could use symmetry in this case. So symmetry of the region, d, in the x direction, and also symmetry of the function we're integrating, as we'll explain, to show that this is just 0. So I won't talk too much about this, but the idea is just, so the center of mass is just like, if you like put it in 3 dimensions, like in the XY plane, and you put like, you look at the center of mass, you can balance the entire plate on top of the center of mass. So if you think about it, there's an equal amount of mass to the left and to the right of x equals 0, right? The y-axis, because mass only depends, density only depends on y. And so there's the same amount of mass on both sides because it's symmetrical in the x direction. And well, I'll talk more about it, but that's the idea behind this. But if you integrated that yourself, you would also get 0. The thing is, it's going to be a lot faster to use symmetry. You can skip the entire integral, basically, which is nice. So then the y-coordinate of the center of mass is going to be 1 over the mass times the integral over d of y times the density. So 1 over d is 15 over 8. Use the same bounds. Integral x goes from -1 to 1, y goes from 0 to 1 minus x squared. And y times the density is y times y, which is y squared. And this time we can't use symmetry because there's no symmetry in the y direction about the y-axis. And so we get 4/7 when we do that integral with a bit of simplification.
Wait, I'm sorry. Where did you get the when you were finding the x bar? Where did you get the x, y, and in the y bar? Where did you get the y squared from?
So what we're integrating for x bar is x times the density. And so that's x, and the density is y.
Okay, I got you.
Yeah, yeah. So it's 1/mass times the integral of x times the density for x bar. And then y squared is y times the density, which is y. Okay. And so our center of mass is going to be x is 0, y is 4/7. Okay, so how we're setting up the integrals, the finding the bounds and everything, that's the previous few chapters we looked at. But the things to remember from today are, if you have a density function, right, could be mass, population, charge, etc. If you want to find the total amount on some region, you integrate the density over that region. So if you want to find the mass, you integrate the mass density. You want to find the charge, you find the charge density, integrate the charge density, etc. The center of mass only works for mass in this case, but the center of mass is 1/mass. You have to find each coordinate separately. So the x coordinate is 1/mass times the integral of x times the density. Y coordinate is 1/mass times integral of y times the density, etc. So those are the two things to take away. Two main things. One more thing I want to mention. I'm not going to do an example here, but it's in the homework, so I'll mention it. And I believe there's a question in the review as well. Is average value. So I'm going to write it for R2, but it works equally well for R3. So if you have a function, f of x, y, I believe in the review questions, it's usually density, but it doesn't have to be. So if you have some function and you want to find the average value over some region D, on some region D in R2 in the plane. So what you do is you integrate the function over D, and then you divide by the area of D. Whoops. So we're looking for the average over here. So the integral over D of the function gives you sort of like the total, and then you divide by the area of D to get like the average value of the function on there. And remember, this is important. The area of some region in R2 is just the integral of the constant function 1. So for function of two variables, the average over region D and R2 is just 1 over the area of D times the integral of the function over D. And just for completion's sake, for functions of 3 variables over regions in R3, exact same thing. So it's going to be 1 over now the volume of the region, because area doesn't make sense for a 3-dimensional region. So we integrate the function over the region and then divide by the volume. And remember, the volume is the same thing. You just integrate 1, the constant function 1, over the region in question. So that's for the average value of a function. Right, you integrate the function and divide by the area or volume, depending on whether it's 2 or 3 dimensions. Okay, any questions about anything today? Or the exam or anything like that? Cool. If not, have a great weekend. Remember, exam review questions are up, and I will post a lecture on the YouTube covering using symmetry to simplify integrals. Trust me, it's going to make your life a lot easier on the next couple exams. It's going to really speed things up, which is going to be important. And yeah, I'll let you guys know when that is posted. All right, have a good one, guys.